Hello, this is video 4 in a series of recordings on alcohols. In the previous videos, we had looked into some of the physical properties and chemical properties. So this video is literally a summary of the reactions, and we also look into the route maps for the changes between the functional groups. So in organic chemistry, it's very important to understand that you can move from one functional group to another. So you can convert the functional groups, and it's very easy to know the conversions if you are revising regularly. But when you have got a lot of functional groups that you've covered, then it all starts to blur and merge into one another. So it's very important to have a mind map or a route map that shows you the conversion routes for the different functional groups. So that's what we're going to be looking in this particular video. So very quickly, if we just go over what we covered in the previous video. So where I left off in the last video, I left you with a question. We were looking at the tertiary alcohols, and then I gave you an example of butane 2-ol. So that was a trick there. You had to identify whether this will undergo oxidation or not. So the question was, is it a primary or secondary or a tertiary alcohol? So the way to answer, and I hope you have answered it correctly, is by looking at the carbon which is bonded to the OH. Is this carbon bonded to 1, 2, or 3 carbons? So as we can see, it's bonded to 2 carbons, therefore this is a 2-degree alcohol. When you oxidize an alcohol, it occurs in presence of potassium dichromate, in presence of dilute sulfuric acid. So we talked about in the previous video that it will form water. Now, oxygen from here, 1 hydrogen from the OH, and 1 hydrogen from the same carbon which is holding the OH. So what we left out here, so if I just write, so we've got CH3, then we've got CH2, then we're left with no carbon. On this carbon, we're left with no hydrogen and 1 oxygen here. Now we know oxygen should now have a double bond, so I'll put a double bond to that, and then I've got CH3. So this one is 1, 2, 3, 4 butane. So butane 2-ol got converted into, I have got here butane, and it's ketonic functional group because there is no hydrogen attached. Because it's formed a ketone, the ending of the name will end in an -one. So butane -one. You don't need to put 2 on there, because if you don't put the 2, it's assumed that it is at position 2. Whereas if it was at position 3 or any other position, you would have called it with that. You would have used that number to identify the position. So that's what we had looked into the previous video. So overall, the alcohol oxidation is, if you have 1-degree alcohol, you can oxidize them into an aldehyde. And if you want the reaction to stop at the aldehyde, you would distill away the product. So this was RCH2OH would undergo oxidation to give you RCHO, and we said it would form water. So if I just put K2Cl2O7 in presence of H2SO4, and we said that was the first reaction. Here you would just use distillation method, and if you did reflux, then the RCHO that's formed would further get oxidized to give you RCOOH. That means overall the reaction, if you add up these equations, cross out the common things on both sides, then you are left out with RCH2OH plus, I've got 2 lots of oxidation process, so 2 steps there, so I show 2 here. I've crossed out the aldehyde, so my final product is the acid plus H2O. So if you're asked the overall equation for a 1-degree alcohol, you would show this. For a 2-degree alcohol, so you would have that. So 2-degree alcohol, you would put K2Cr2O7 in presence of H2SO4, H, and O removed. So now you are left with RCr double bond O. The carbon, the C double bond O, is attached to no hydrogen, therefore this is your ketonic functional group, and the name ends with the O. So as in the previous example, we called it butanone. So that was in a nutshell primary and secondary. So if you want the reaction to turn all the way to carboxylic acid, for primary you would do reflux method. 3-degree alcohol, we said it will not undergo any oxidation. So that was in a nutshell the oxidation reactions, whereby the color change is always from orange to green. So the orange to green color indicates that the oxidation has happened because the dichromate ions get changed into chromium ions. And in the previous video, we'd looked into some of the redox equation behind that color change. We have to look into the uses of alcohol. Ethanol is the ingredient in the alcoholic drinks. It's used as a solvent, fuel, chemical, feedstock. Feedstock means that it's the starting material to form many other useful compounds or products. So methanol is similar. It's used in petrol because it burns very well, and it's also used as a feedstock. So you would have to learn these uses of alcohol. These are common 1 or 2 mark questions. So overall, we've looked into the summary. To summarize, we've looked into alcohols. So in the first video, we had looked into the classification of alcohol. We had studied that alcohols can be 1 degree, 2 degree, 3 degree. We know alcohol's general formula is CnH2n. So CnH2n plus 1 OH. Their general name is alkanol. So you end the name as an ol. 1 degree, 2 degree, 3 degree, depending on how many carbons are attached to the carbon holding the OH. So if the carbon holding the OH, if that carbon is attached to 1 carbon, then you call it 1 degree. If that is attached to 2 carbon, then you call it 2 degree. If that carbon is attached to 3 carbons, then you call it as 3 degree alcohol. We also looked into the physical properties of alcohol, and we compared the physical properties. As mentioned before, whenever we talk about physical properties, especially boiling point, then we'd looked into the volatility of alcohols. We'd also looked into the solubility of alcohol. In all of these, it's very important to note that what is the structure, what is the bonding, especially the intermolecular forces. So we said that these all contain hydrogen bonding. Because they have hydrogen bonding, therefore their boiling point is high. If the boiling point is high, they're not that volatile as compared to an alkane with the same number of carbon atom. These alcohols are soluble in water because they can form hydrogen bonding with water. So this bit was all covered in the first video. In the second video, we looked into a few of the chemical properties. We looked into the combustion reactions, whereby the alcohols are burning to form carbon dioxide and water. It's a complete combustion, so they don't form much carbon monoxide there. Alcohols, we had also looked into the elimination reaction, whereby we had dehydrated the compound, the alcohol, with concentrated H2SO4 or concentrated H3PO4, and this resulted in the formation of alkenes. We'd also looked into the substitution reactions of alcohols and substitution with HBr or HCl and H. So when we had looked into these halides, what we had done was we realized that these were prepared in situ, and the reagent that we used was NaX plus H2SO4, concentrated H2SO4, and they resulted in the formation of haloalkanes. So that's when you do substitution reaction. So these three reactions we looked in video 2. In video 3, we've looked into the oxidation reaction of alcohols, whereby 1 degree gives you an aldehyde, which can then be converted into a carboxylic acid. The color changes orange to green. 2 degree forms a ketone, and 3 degree will not undergo any oxidation. So this is in a nutshell the summary of the reactions that we've covered in the first 3 videos. Overall, based on these sort of reactions that you've covered so far, you can start building your own route map. So if you start off with alcohol, you can think, can I convert an alcohol into which functional group? So if you look at the previous section, we've talked about alcohol can be converted by combustion into carbon dioxide and water vapor. They can be dehydrated into alkenes. So what you could now do is we can convert alcohol into alkenes. So that is your route map. You can do that, and you would need to put your reagent here. So you've got concentrated H2SO4 or concentrated H3PO4. We'd also seen that, so that part is done. We've also seen that you can substitute with NaX. So if you have NaX plus H2SO4, and this would produce HX in situ. So you're writing these things as a memory, kind of something to remind you that you will get a haloalkane in this reaction. And when you put in situ there, that would jolt your memory that actually the HX is not a reagent here, but you've actually taken NaX and H2SO4. So that reaction's done. The third reaction is your oxidation reaction. So now you've got that. If you start to think, you will get either an aldehyde. So if it is a 1 degree alcohol, 1 degree alcohol gives you an aldehyde. Aldehyde will then give you a carboxylic acid. So what you're doing is you're seeing the way in which you can go from an aldehyde to a carboxylic acid. So if it is a 2 degree alcohol, you would get a ketone on oxidation. And you can also have, if I took a 3 degree alcohol and if I oxidized it, I would get nothing. You could also put combustion reactions. So if you combust, so that's burning, so you would get carbon dioxide and water. So this is a route map for just one functional group. Now, when you study the next functional group, you could build a route map for that functional group and also then try to integrate the 2 route maps. And a very good way of revision would be to try to draw the route map without actually revising the topic, and that would try to bring out what the areas that you're confused in or the areas that you've forgotten. So this is a very important skill to develop for organic chemistry. So thank you for listening, and I hope by watching the series of 4 videos, the topic is slightly clearer, but a lot needs to be practiced by solving past exam questions and by practicing drawing the route map. So I wish you all the best, and I look forward to meeting you again with my new video series. Thank you for listening.